There are more planets in the observable universe than grains of sand on every beach and desert on Earth combined. And that statement, which sounds like the kind of hyperbole someone tosses out to impress at a casual gathering, is validated by real astronomical calculations and backed by data collected from telescopes that have spent decades sweeping the sky. We are not talking about millions of planets. We are not talking about billions. We are operating on numerical scales that simply do not exist intuitively for the human brain, quantities that must be compared to something concrete and visible just to begin making any kind of sense. If you walked to the nearest beach right now and started counting every grain of sand that fits in the palm of your hand, it would take hours just to get through that single handful. Multiply that by every beach on the planet, every desert, every dried-out riverbed, every river, every ocean floor, and you would still fall profoundly short of the number of planets that likely exist in this universe. It is a real number, estimated with scientific rigor, and it carries an immediate and inevitable philosophical consequence. Given that planets are the places where life emerges, the idea that Earth is the only address in the cosmos where anything living exists begins to seem not merely unlikely, but almost mathematically absurd. The Milky Way, the galaxy we call home, contains between 200 and 400 billion stars. That number alone is something the human brain simply files away under the category of very large, and archives without ever truly processing. But what transforms everything is what the last few decades of astronomy have revealed about those stars. Most of them have planets, not some of them, not the ones under special conditions. Most of them. Even the most conservative estimates suggest there are at least 1 trillion planets within the Milky Way alone, and that a great many of them orbit their stars within zones where temperatures could allow liquid water to exist on the surface. And the Milky Way is just one among the 2 trillion galaxies that astronomers estimate exist in the observable universe, which is itself only the portion of the universe that light has had time to cross to reach us in the 13.8 billion years since the Big Bang. When you begin multiplying these numbers, you arrive at something for which human language simply has no adequate representation. These are quantities that only carry meaning inside equations, never in sentences. And it is precisely here that the question begins to truly unsettle. Because if this nameless number of planets exists, and if planets are the environments where chemistry organizes itself into biology, what is the real probability that Earth is the only place where that organization ever occurred? The honest answer, backed by the available data, is that this probability is vanishingly small, almost indistinguishable from zero on the cosmic scale. This is not scientific optimism. It is not astronomical romanticism. It is statistics applied to scales that defy all human intuition. And the more our astronomical instruments evolve, the more that probability of absolute solitude shrinks in the face of the data. The most powerful argument in favor of life beyond Earth does not come from signals captured from distant stars. It comes from Earth itself, because life on our planet is not some fragile thing that survived through an unlikely sequence of perfect coincidences. Life on Earth is extraordinarily stubborn, adaptable, inventive. Life thrives at hydrothermal vents on the ocean floor, where water temperatures exceed 300 degrees Celsius, and the pressure would crush any structure ever built by human hands. Life exists in the cracks of rock kilometers underground, where no sunlight ever reaches, and the only available nutrients come from chemical reactions between minerals and water. Life exists inside abandoned nuclear reactors, where organisms have evolved to metabolize radiation itself as a source of energy. Life exists in the driest deserts on Earth, where decades pass without a single drop of detectable rainfall. These organisms, collectively known as extremophiles, are not mere biological curiosities. They are experimental proof that life does not require ideal conditions to function. It requires only available energy and sufficient time. This realization has fundamentally changed everything. Irreversibly, it has transformed the way scientists define habitability. For decades, the search for life beyond Earth focused exclusively on planets nearly identical to our own. Same distance from the parent star, same abundance of liquid water on the surface, a comparable atmosphere. But if life on Earth thrives under conditions we once considered lethal to any living thing, then the concept of the habitable zone must be far broader than the original vision ever suggested. When that concept expands, the number of environments across the universe where life could have emerged grows in ways that make Earth's cosmic solitude increasingly difficult to defend on rational grounds. We are no longer searching for a needle in a haystack. We are beginning to realize that perhaps the entire haystack is made of needles, and that the right question is no longer whether life exists out there, but why we have not found it yet. The first thing we must understand about life is that it is not an exclusively Earth-bound phenomenon, at least not in terms of its ingredients. The raw materials of biology, the fundamental building blocks of everything that exists and grows and replicates on this planet, are scattered across the entire cosmos. Amino acids, the molecules that form proteins and serve as essential structural components of every known form of life, have been detected in meteorites that crossed the solar system and landed on Earth billions of years ago. Those meteorites came from distant reaches of space, carrying complex organic compounds that the chemistry of the universe had assembled long before Earth itself existed. The implications of this are profound. Life did not invent its own chemistry from scratch. It seized upon ingredients the universe had already been producing on a vast scale, in gas clouds between the stars, in asteroid belts, in comets drifting through space for billions of years. Life, in a very real sense, is an expression of the chemistry of the cosmos, not an anomaly within it. Hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur, the 6 elements that make up virtually all known biology, are among the most abundant elements in the universe. They are forged inside stars and scattered across space when those stars die in cataclysmic explosions we call supernovae. Every atom of carbon inside your body was forged in the core of a star that no longer exists, cast across the cosmos before eventually becoming part of the solar system, of the Earth, and then of you. This is not poetic metaphor. It is verifiable astrophysical chemistry. The universe manufactures the ingredients of life as a natural consequence of its own nuclear reactions, and those ingredients appear everywhere telescopes have ever turned to look. Molecular clouds between the stars have been mapped by radio telescopes, revealing a surprisingly complex chemistry, with multi-atom organic molecules forming naturally in the vacuum of space, far from any planetary surface. But the most intriguing evidence that life may exist beyond Earth does not come from distant stars. It comes from our own solar system, from places that just a few decades ago we considered utterly hostile to any form of biology. Enceladus, one of Saturn's moons, measures little more than 500 kilometers across, its surface blanketed in brilliant white ice. But beneath that ice lies a liquid ocean of salt water, kept warm by the gravitational forces Saturn exerts upon the moon's interior. And that ocean is not simply lying hidden in silence. It actively expels its contents into space through geysers that erupt across the polar surface, launching water vapor and ice particles hundreds of kilometers into the sky. A space probe flew directly through that plume and detected, among other things, complex organic molecules, molecular hydrogen produced by hydrothermal reactions on the ocean floor, and nitrogen compounds. It is, in essence, the very type of environment found at the bottom of Earth's oceans, where life thrives in abundance without a single ray of sunlight. Europa, one of Jupiter's largest moons, presents a remarkably similar picture. Its surface is a crust of ice, crisscrossed by fractures that reveal something liquid moving beneath. Estimates suggest that the ocean beneath Europa's ice reaches depths of over 100 kilometers and contains more liquid water than all of Earth's oceans combined. The pressure, chemical composition, and temperature of that ocean are, in many respects, comparable to the conditions found in hydrothermal zones at the bottom of Earth's own oceans. If life on Earth arose in those zones, a hypothesis supported by geological evidence, then Europa possesses every fundamental ingredient that biology would need to at least attempt to begin, and it does not stand alone in that category. Ganymede, another of Jupiter's moons, likely harbors a subsurface ocean as well. The solar system, which for decades we imagined to be essentially Earth and then rocky desert and gas, is revealing itself to be surprisingly rich in aqueous environments. Mars remains a serious candidate, though for reasons quite different from those science fiction once suggested. Today, Mars is cold, dry, and cloaked in an atmosphere so thin that surface pressure is less than 1% of Earth's. But the geological evidence is unambiguous. Around 4 billion years ago, Mars had roaring rivers, lakes, and possibly an ocean covering part of its northern hemisphere. That period coincides precisely with the emergence of life on Earth. If life appeared here under those primitive conditions, Mars, during that very same era, harbored remarkably similar ones. The question scientists are now pursuing is whether life that may have arisen on Mars during that ancient age survived the planet's catastrophic transformation, sheltered in subterranean pockets where liquid water may still exist today, warmed by the geothermal heat of the Martian interior. If life is so probable, if the ingredients exist everywhere, if the solar system already holds several plausible candidates, and the galaxy harbors trillions of planets, then a question emerges, one that has haunted us for decades. Anyone who thinks seriously about this, where is everyone? That question, posed with such stark simplicity, is known as the Fermi paradox. And it is perhaps the most profound question in modern science, not because there are no possible answers, but because every available answer carries implications that range from deeply comforting to deeply disturbing. If the universe holds the conditions for life in abundance, if it carries billions of years of history during which civilizations could have risen and spread, and if technology exists that would allow communication across galactic distances, then the silence we observe when we turn our instruments toward the cosmos demands an explanation, not ignorance. The simplest answer, and the one many scientists consider most likely, is that we have found no other signs of life simply because we haven't looked long enough. Long enough, with instruments sensitive enough. The universe is staggeringly vast. Our detection technology is relatively primitive, and the period during which we have actively searched for signals from civilizations beyond Earth is infinitesimal compared to the timescales of the galaxy. The Milky Way stretches more than 100,000 light-years across. If a civilization 50,000 light-years away transmitted a radio signal today, that signal is 50,000 years from reaching us. The silence so far may simply mean the time has not yet come, that the signal is still in transit, crossing the void at a speed no technology has ever surpassed. A second possibility: microbial life is common, but intelligent life is extraordinarily rare. It may be that biology emerges with some regularity across the universe. That bacteria and simple organisms arise in the subterranean oceans of icy moons and on planets with the right conditions. But that the leap from single-celled organism to technological civilization is so improbable, it has happened only a handful of times in this galaxy. The complexity of multicellular life, of the nervous system, of intelligence that wields tools and then builds science, may be a sequence of developments, each one vanishingly unlikely, making the final product something rare, even in a universe teeming with simple life. If that is the case, finding microorganisms on Enceladus would be an absolutely historic discovery, but it would not explain the silence of civilizations. There is also the idea scientists call the Great Filter, the notion that somewhere along the path from simple life to technological civilization, there lies an obstacle that almost no species manages to overcome. That filter may lie in our past or in our future. If it lies in the past, if the hardest leap has already been cleared by life on Earth, such as the emergence of the nucleated cell or sexual reproduction, then our very existence is extraordinary, and other civilizations likely never made it this far. If the filter lies ahead, if there is some obstacle that technological civilizations almost inevitably cannot survive, then the silence carries a very different weight. But it is essential to acknowledge that we have insufficient evidence to know whether the filter exists at all, and where it might be located. This is rigorous speculation, not scientific certainty, and must be treated as such. The most compelling interpretation of the cosmic silence is that advanced civilizations may be communicating or manifesting themselves in ways our technology is not yet capable of detecting. Our current search focuses primarily on radio signals because that is what we ourselves developed as a means of communication. But a civilization thousands or millions of years ahead of us in technological development may be communicating with lasers at specific frequencies, with modulations across regions of the spectrum our instruments do not systematically monitor, or through methods we have not yet even conceived. In that scenario, we would be in the position of someone trying to pick up a high-definition television broadcast using a battery-powered radio. The tool is simply not calibrated for the signal. This does not dissolve the paradox, but it is a compelling reason to take the search seriously, with ever more sophisticated instruments and ever more diversified detection strategies. The James Webb Space Telescope represents the moment when the search for life beyond Earth ceased to be entirely philosophical and became observational in a way that previous generations of astronomers could only dream of. This instrument, launched in December 2021 and operational from 2022, has the capability to analyze the chemical composition of the atmospheres of planets orbiting stars tens of light years away. It does this by observing starlight as it passes through a planet's atmosphere during a transit, then breaking that light into its component frequencies to identify the molecules that absorbed it. Each molecule absorbs specific wavelengths, acting as a kind of chemical fingerprint that the telescope's instruments can identify across distances previously unimaginable. What scientists seek in this analysis is not any single organic molecule in isolation, but combinations of molecules that should not coexist on a planet without active life, because non-biological chemistry would destroy them rapidly. The clearest example is the simultaneous presence of oxygen and methane in a planet's atmosphere. Oxygen reacts chemically with methane, and the two consume each other on geological timescales. In an atmosphere with no constant replenishment, they would not coexist for long. If James Webb detects both simultaneously in a ratio that cannot be explained by any known geological process, the most economical explanation is that something living is continuously producing these molecules. It would not be definitive proof of life, because science rarely operates with definitive proof on first instance, but it would be extraordinarily compelling evidence, triggering an intense wave of investigation across multiple telescopes and independent methods of observation. The first atmospheric analyses of candidate exoplanets have already begun. And while the initial results remain inconclusive, the methodology is proven and the sensitivity of the instruments grows with every new cycle of observation. The most studied candidate at this moment is the TRAPPIST-1 system, a red dwarf star 40 light-years away, with 7 confirmed planets in orbit, 3 of which lie within the habitable zone. 40 light-years. It may sound like a vast distance, but in terms of remote spectroscopic analysis, it is cosmic next door. These 3 planets have sizes and densities comparable to Earth, and they occupy an orbital configuration that allows frequent, regular transits, making them ideal for exactly the kind of analysis James Webb performs. If any one of them harbors an atmosphere bearing the chemical signatures of biological processes, we will have the first concrete evidence that life exists beyond Earth, a discovery that would permanently redefine humanity's place in the cosmos, in a way no other scientific event has ever done so directly, so personally. The search also turns inward toward our own solar system, with growing urgency. The Europa Clipper mission, launched in October 2024, is now on its way to Jupiter, with the specific goal of characterizing Europa's ocean in extraordinary detail and assessing its habitability. It will execute more than 50 flybys of the Moon throughout its mission, mapping the thickness of the ice, measuring the magnetic field, analyzing the composition of the plumes, and evaluating whether the subsurface ocean holds the ingredients and the energy conditions necessary to sustain biology. It will not land, it will not drill through the ice, but it will produce the scientific map that makes a future drilling mission possible. Direct. At Enceladus, the plumes that erupt naturally into space represent an extraordinary advantage. A probe could fly directly through them, analyzing the contents of the subsurface ocean firsthand, without having to breach a crust of ice kilometers thick. What is remarkable about this historic moment is that, for the first time, we have as many identified candidates as we have the specific instruments needed to investigate them systematically and deliberately. It is no longer a question of whether the search is technically possible. It is a question of when the data will arrive and what it will reveal. The coming decades may be the period in which humanity finally obtains its first evidence that it is not alone in the universe. And that moment, when it arrives, will not appear merely in an abstract, in a scientific journal. It will be a rupture in the way the human species understands its place in reality, comparable to when we realized that Earth was not the center of the solar system, or that the universe had a beginning in time. Let us return to the beginning, to the impossible number of planets that exist in this universe, and to what that number means for you right now, in this moment. If the probability of our being the only living beings in a cosmos with that many addresses is statistically close to 0, then the question is no longer whether life exists beyond Earth. The question that truly changes everything is what that near statistical certainty means for how we relate to our own place in the universe. And here, astronomy ceases to be an abstract science and begins to say something directly about what we are and about why that matters now, not merely in some distant future when confirmation finally arrives. If there are other forms of life in this universe, and the available evidence strongly suggests there are, they are, in all likelihood, overwhelmingly microbial bacteria in the subsurface oceans of icy moons, chemosynthetic organisms clustering around hydrothermal vents on distant worlds. Microscopic colonies enduring within cracks in rock beneath surfaces that appear barren from the outside. Simple, single-celled life that does not think, does not broadcast radio signals, and does not build telescopes. It is almost certainly the most common form of life in the cosmos, and that diminishes nothing of the magnitude of what it would mean to find it. A bacterium on Enceladus would be the most important revelation in the history of human science, because it would prove something that remains, for now, mere inference, that life is not an accident exclusive to Earth, that it is a process the universe generates in independent locations. That biology is a property that emerges from cosmic chemistry, not an exception to it. But there exists the possibility, small in probability and colossal in implication, that intelligent life also exists somewhere in this galaxy or in another. Civilizations that rose and built language, technology, science, art, and questions about their own existence. Civilizations that perhaps also turn their instruments toward the cosmos and ask themselves the same question we do, whether there is anyone else out there. The silence between us and them, if they exist, is simply a matter of scale and the speed of light. A signal sent now from a planet 100 light-years away will reach us in 100 years. The cosmic conversation, if it ever happens, will be slow by physical necessity. Not for any lack of interest from the possible participants, and the fact that we have received nothing yet simply means that the universe is vast, and we are very new to this search. What changes when you accept that we are probably not the only living beings in the universe is subtle but real. Earth ceases to be an isolated fortress in the void and becomes instead a single point within a far denser fabric. Life, as a process, is something the universe does. We are a local expression of that process, as local as the planet we inhabit within a single galaxy. Among 2 trillion galaxies. But local does not mean without value. It means unique in the sense that this specific version of life, this form of consciousness that looks upward and questions its own existence, is happening here, now, on this planet, in this age. And whether Earth is the sole conscious place in the cosmos or merely one among many, it is something that deserves to be treated with the gravity and care that the privilege of existing demands. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Human intelligent life, as we know it today, is perhaps 300,000 years old. We are very new. Our instruments are very new. The search itself is very new. And yet, in this vanishingly brief cosmic window, we have reached the point of analyzing the atmospheres of planets 40 light-years away, of sending probes to moons with potentially habitable oceans, of detecting organic molecules drifting in gas clouds between the stars. The definitive answer to whether we are alone has not yet arrived. But the direction the data consistently points toward is a universe where life is not some rare artifact of a single, unrepeatable accident. And when that confirmation comes, it will be the kind of discovery that reshapes how future generations see themselves within the cosmos. The question that remains for you now is this: if tomorrow the existence of microbial life on Enceladus were confirmed, what would that change in the way you look up at the night sky? Leave your answer in the comments, because this conversation deserves to happen. And if you want to keep exploring the universe with the depth it deserves, subscribe to the channel and share this video with someone who also turns their face to the sky and wonders if there is anyone else out there doing the same from the other side.